The Internet is built upon a single premise. Ask and you shall receive. Request and you shall get a response. The requests library handles these digital conversations with remarkable grace. Today we will use the requests library to build HTTP clients that know how to ask servers for exactly what you need. Connection established. Transmission begins.
HTTP clients send HTTP requests and receive HTTP responses. In Python, the most popular HTTP client is the requests library. May I introduce you to the 4 primary HTTP methods. GET retrieves data from a specified resource. POST sends new data to create a resource. PUT updates existing data. And DELETE, well, I think you can deduce its purpose. Each request requires a method and a URL. The method specifies what action to perform. The URL specifies where. Headers and data are optional parameters that provide additional information. We begin by making a simple GET request to a web server. But first, download the requests library. A simple pip install requests will suffice. Next, import the requests module. Now, send a GET request to GitHub's API and store the response. The response object contains everything the server wishes us to know: status code, headers, and content. Let us inspect the response object, the server's reply to our digital inquiry. The status code tells us if the request was successful. A status code of 200 means all is well. Other codes are less encouraging. The headers property provides metadata about our response. Think of it as the server's way of adding footnotes. And finally, the text property contains the actual data we requested. The moment of truth. Run. Sometimes we need to send data to a server. That is where POST requests come in. Allow me to demonstrate with http-bin.org, a testing server designed to analyze HTTP requests. We prepare a dictionary with our data, then send it using the POST method. The server responds with a detailed report of everything it received. Think of it as an HTTP request anatomy lesson. Run. The data parameter automatically converts our dictionary into properly formatted data. POST is quite considerate that way. Now that we can send data to servers, we need a way to provide specifications about that data. For instance, is our payload JSON or XML? What type of response do we expect back? This is where headers enter the picture. Headers are the metadata of the web. They allow us to send additional information with our requests, vital context for proper data handling. The most common header is user agent, which identifies your application to the server. It is considered polite to identify yourself properly, after all. When servers receive requests with headers, they respond with headers of their own. Observe. Run. Critical metadata transmitted with every request and response, as it should be.
I suspect there is a high probability you require a Python-themed shirt. This is not merely a GET request. This is a MUST request. Visit the Socratica store to post your order. Warning, these shirts have been known to trigger endless conversations about coding. That is not a bug. That is a feature.
One format commonly used for data exchange is JSON, JavaScript Object Notation. The requests library makes working with JSON easy breezy, lemon squeezy. When sending data, use the JSON parameter instead of data. The library will handle all the necessary encoding. When receiving data, the JSON method transforms the response into a Python dictionary. Run. A perfectly logical transformation. In an imperfect universe, requests do not always succeed. Servers may be unavailable. Resources may not exist. Permissions may be denied. The status code tells us what went wrong. A code of 404 means not found, the digital equivalent of trying to open a door that does not exist. A code of 403 means forbidden. This door exists, but is firmly locked. You could check these codes manually, but why not automate? The raise for status method will raise an exception if something goes wrong. Note that this requires a try except block. Run. Skip this convenience method, and you will be forced to inspect status codes, like a human. If you are making multiple requests to the same server, consider using a session object. A session object persists certain parameters across requests. Create it once, and it will remember your headers, authentication, and other preferences. No need for repetition. No need for redundancy. No need for... You understand. Let us create a session object and observe its behavior. Instead of calling methods on requests, we now call them on our session object. The session maintains our configuration across all requests. Let us verify this behavior. Observe. Both requests contain identical authorization headers. Run. No need to re-authenticate. The session remembers. Authentication is the digital handshake of the web. The requests library supports multiple authentication protocols. Basic authentication is the simplest, though basic is an understatement. It transmits credentials with minimal encryption, disappointingly simple to decode. Nevertheless, let us observe the protocol in action. First, without authentication. Run. Access denied. Then with proper credentials. Run. Access granted. Recommendation: use token-based authentication in production. The requests library has features for more demanding tasks. Consider streaming downloads, useful when dealing with large files. Set stream to true. Run. And the data arrives in manageable chunks. You may also specify a timeout, quite useful when servers are being less than responsive. Run. These features exist for those who require greater control over their HTTP communications. You may not need them today, but when you do, they will be waiting. Cookies store small pieces of data between requests. They function like digital name tags, identifying you to the server. The requests library handles these identifiers automatically. When a server sends cookies, they are stored in response.cookies. When you need to send cookies back, use the cookies parameter. Each request presents them. Each response may update them. Let us observe their exchange. Run. Files must occasionally travel across the network. The requests library handles this case as well. To upload a file, provide it in the file's parameter. To download a file, stream the content and process it in chunks. This prevents memory overload when handling large files. Binary mode ensures data integrity during transfer. Run. The streaming approach maintains constant memory usage. Each chunk arrives, processes, and clears the buffer. File transfer complete. No bytes were harmed in this demonstration. Network requests often benefit from taking the scenic route. Proxy servers provide these alternative pathways. Configure them with a simple dictionary, each protocol paired with its proxy. The requests library will then route your traffic accordingly. A proxy adds an extra step to the journey. But as they say in network architecture, the shortest path is not always the most optimal.
You are now equipped to communicate with servers across multiple protocols. The request library handles the complexity. You handle the logic, and the servers, well, they handle whatever they handle. Transmission terminated.